Good evening. Welcome to the June meeting of the Baton Rouge Astronomical Society. And keeping what we normally do, we're having our speaker first. Our speaker is Zach Yarbrough. He's a graduate student at LSU, and he's going to be talking about LIGO and gravity waves. So, Zach?
Technically, gravitational waves, difference.
Yeah, okay.
We call them both. It really is a matter of personal preference, right? Coke, Pepsi, gravity wave, gravitational wave. So, you're going to get a groan from one half of the collaboration, but whatever you do. Thank you, John, for the introduction. Hi, everybody. It's a pleasure to be here. My name is Zach. I just finished up my first year at LSU in the PhD program, and I'm working in the LIGO collaboration on gravitational waves and the instruments that we use to detect them. It's a pleasure to be here. My first time with the group, but you all have been tremendously welcoming and already asking great questions and seem to be really excited. So I'm excited to share a little bit about what it is that I do as a graduate student, and then I hope I can speak to the really impressive scope of our collaboration and the discoveries that we've made in the past, what it took to get there, where we are now, and where we hope to be in the near future. So to maybe draw the target on the wall before we attempt to take something away from the presentation, I'd love to lay out what my goals would be. I will be a very happy person if at the end of this talk you can describe what a gravitational wave is and what causes them, if you can appreciate what went into the first detection of gravitational waves, and if you can be excited about the future. So these are my three goals. You don't need to memorize anything about Einstein's field equations. I'm not going to quiz you about any of the gravitational wave events we've seen so far. I just hope you guys can really appreciate it. I can come up with something really quick if you want. So, but these are really what I would love us to be able to do at the end of the talk. And let me get a timer going here, just so I don't keep us all here until midnight.
Be cool.
So I teach the astronomy lab at LSU as a graduate student. That's how they pay me, and it's one of the perks of the job, really. I deal with a lot of undergrads on a weekly basis who are not necessarily physicists. They're scientists. I get a lot of psychology majors. I get a lot of computer scientists. I get a lot of English majors, and I get a lot of business majors. Those are my big four. They might not be physicists or astronomers, but they are nevertheless very excited about what it is that we do in our field. And when I teach the gravitational wave section, it's one of my favorites, if not one of the most challenging. Because the question that they will often ask, first thing, is what is a gravitational wave? What is a gravity wave? Can I see it? Can I touch it? Can we feel it? Are they happening right now? And these are all fantastic questions that take a lot to answer. And the tricky thing is, even though these inquiring minds, these scientists in their own right, are asking very good questions, oftentimes we divert to things like really complex math or unnecessarily grandiose explanations of what it is that's going on when we describe a gravitational wave. That name elicits to me things like a surfer riding on a cosmic wave or a jovial greeting from the universe, like we can see here. And in their own right, you could consider them to be those fun, interesting things. But what I tell them, and from a perspective of tangibly describing this very complex thing that has been in speculation for over 100 years in gravitational waves, we say that they're ripples in space-time caused by energy released from an accelerating mass. Any mass of any size undergoing an acceleration. Your car when you got on the highway to drive here, the space shuttle as it launches another satellite, the hands of a maestra conducting her orchestra. These are all accelerating masses, and these are all, by definition, releasing gravitational waves. Now, they're going to be incredibly small. These gravitational waves are going to be absolutely minuscule, and we'll talk about the scale of the gravity waves produced by astrophysical events and understand how small those are to understand how really impressive it is that we can actually directly detect them with LIGO. But this idea, energy released from an accelerating mass, is at the core of what we do. And that's the definition. No ifs, ands, or buts, no speculation. As I stand, as I move, as you move, we are creating gravitational waves. Gravitational waves historically were first predicted by this handsome fella in 1916 in one of his papers on general relativity. He did this not with a fun computer animation software or even computers to run his code or do his math, but with some very intense tensor math that we teach to upper level graduate students. That is kind of one of the stopgaps of explaining the gravitational wave, gravitational physics to like the interested public, or students taking a class because they have to be there, but who are nevertheless very interested in the things we're talking about. So these lovely, lovely professors at LSU, this is my advisor, Gabby Gonzalez, on the left, and her husband, Jorge Pullen, on the right. They use this math to torture graduate students endlessly, but we do love them for it because this math has been around longer than many of us. And this prediction over 100 years ago has withstood ebbs and flows of public confidence, ebbs and flows of scientific pokes and prods, because people, including Einstein himself, remained unconvinced for quite some time that gravitational waves did not exist. So when we see these funny symbols, I think it's, first of all, it's a beautiful equation, but it does take a lot of upper level physics to understand. So it is prohibitive in that way. But if we look at it just as one side of the equation telling space how to move, and the other side of the equation telling mass how to move, we can begin to understand the interplay. Mass tells space how to warp, and then space tells mass how to move. So what that looks like in a little bit more visual detail, as opposed to numbers and mathematical symbols, is in the presence of nothing. When there's no mass present in the universe, we have a flat plane. And this is space-time here. That's what this equation describes. If the mass term is 0, we have everything as being completely flat. And in the presence, there we go, in the presence of something massive, an astronomical body of any variety, shown here, Earth, of course, it curves space-time around it as the presence of mass dictates. So what we see as we involve ourselves with gravitational wave research is the interstellar tango of compact bodies in binary systems. That is what we have seen so far from 2015 to the present. Compact bodies, either a neutron star, a black hole, one of two of each, or one of the other, in this kind of doom spiral, if you will, getting closer and closer and closer to one another, releasing energy from their orbits in the form of gravitational waves. Kind of lovely animation here. The natural question then is, if we've known about gravitational waves since 1916, we've done the math, people have remained somewhat convinced, there's always been a staunch advocate of some kind. If we've known about them since 1960, what took so freaking long for us to detect 2015, September 14th, 2015 is the date of the first gravitational wave detection. Not to spoil the rest of my slides, but that made national news. So if I'm spoiling anything, that's your fault. The natural question then is why did it take so long for us to directly see these things? And the answer is because gravity is extremely weak. Yes, it is the reason the Earth orbits the sun. It's the reason we sit here on Earth and don't float away. We exploit gravity in our everyday lives, but it is still fundamentally the weakest of the four forces. Out of the strong force, the weak force, and the electromagnetic force, gravity is by far the weakest. However, it does have an infinite range. When you're trading one for the other, it doesn't happen perfectly, of course, but the strong force holds the nuclei of atoms together, but it has an incredibly short range. So it can't act on things beyond its scope of influence, its sphere of influence. Gravity has an infinite range, which is why we can observe gravitational waves even after they've traveled billions of light years to come and interact with our interferometer here on a nondescript planet in a nondescript galaxy orbiting a nondescript star. Other way around, but you know what I mean. So even though, as the mass moves under an acceleration, gravitational waves are released, we need these massive compact bodies, compact objects, to produce gravitational waves that we even begin to have a chance at detecting. As these massive objects, many times the mass of our sun, are compacted down through things like stellar evolution and accretion in the case of black holes, they produce a bigger influence over the same mass region. So a black hole with the same mass as the sun will produce a much stronger gravity well because it is so compact. So these objects create the most violent energetic events in our universe. And that is not, we're not seeing these and other things below them. We need energy scales this large to have a chance at detecting gravitational waves because the waves themselves are so small and because gravity is so weakly interacting. So Einstein remained unconvinced for the majority of his life, but he thankfully did not account for these very, very talented scientists and their very, very big machine. And that's what we're going to talk about next, is our beautiful LIGO Livingston here, and what it actually took to measure change in distance over the stretch of 4 kilometers on the order of 10 to the minus 21 meters. We have 3 sites: LIGO Livingston, LIGO Hanford, and this is Kagra in Japan. We also have a 4th site coming online very quickly in LIGO India, and then I neglected to include Virgo, which is the Italian interferometer. To understand these better, this is where the history lesson comes in, to understand really what went into making these operational on the scale that we are today. In 1960, Joseph Weber began the first, what is widely considered the first direct detection experiment for gravitational waves with his Weber bars. These are massive chunks of aluminum that he fitted with detective sensors in an attempt to measure the change in length of the aluminum cylinder as a gravitational wave resonated with the body itself. We now know that even though Weber was very convinced that he did indeed detect a gravitational wave, the thermal noise from the motion of the atoms within the aluminum would be far too high to have a chance of detecting a very, very minuscule gravitational wave. In order to combat that thermal noise, we had experiments by Hamilton and Johnson at LSU in the 70s. This is Allegro. I took this photo like 2 weeks ago. It's still in the basement. And this is very, very similar at scale. This is also just a gigantic piece of aluminum suspended in this vacuum chamber. And these are also light sensors aimed at measuring the change in length of this detector. But it's enclosed in this gargantuan vacuum tube, and it was pumped down to near microkelvin temperatures as best as they could get. I think it was on the order of like 3 Kelvin, what they finally got it down to try to reduce the motion of the particles within the aluminum to have a better chance at seeing a gravitational wave resonating with this gigantic hunk of aluminum. That didn't work. But they sure tried. So this is actually being prepped to be sent to LIGO Livingston, the part of the exhibit. So it'll be after the Science Education Center works. Cool. You can go get up close and personal with it. Around the same time, there were a number of scientists, including Hamilton and Johnson, but probably most notably Ray Weiss at MIT, who was coming up with the idea of, well, all we're trying to do with these gargantuan pieces of aluminum is measure the distance between 2 points. If the distance between these 2 fixed points changes, even by a hair's breadth, that's an evidence for gravitational waves. So what if instead of measuring a single object, we measured the distance between 2 points and we used light as a ruler? Using light as a ruler is another one of my favorite phrases to describe LIGO's capabilities and LIGO's fundamental methods to the scientists in my class. To say that nothing fancy beyond the real structure of the detector. All we are doing is using light to measure the distance between our input test masses or the beam splitter and our 2 mirrors down here. Because we have set LIGO up in such a way that if nothing touches the detector, we won't have a signal. But if those lengths change, even differentially, we will interfere constructively, we will see a signal in our interferometer, and that's evidence for a gravitational wave. So interference, interferometer, that's the etymology. So here is an awesome animation that we're really fond of, really the detection mechanisms at work. So I'm going to let it just play for a second, and then we'll talk about actually what's happening. It's useful to think of light as a wave, which is what we're going to see here. It's split 50-50 by our beam splitter. Half of the light travels down one arm, and half of the light travels down the other. It's an 8-kilometer round trip from our input test mass to our in-test mass, where it is recombined so that the peaks and the valleys match up. That's deconstructive interference. -1 + 1 is 0. Now we're going to see a gravitational wave squeeze and stretch the detector, shifting the locations of the peaks. When the peaks begin to match up, we begin to have light. That's constructive interference. When we have light, when the peaks match up, we produce a signal on our photodetector, and that is how we detect gravitational waves at LIGO. All we're doing is using light as a ruler and using the properties of light and our instrument to set ourselves up for success. By setting our instrument up so that it interferes deconstructively, does not produce light at the output port here, and only produces a signal when gravitational waves physically change the distance between our two test masses, that's how we're able to detect incredibly small fluctuations in space-time itself by using light as a ruler over an 8-kilometer long round trip split down our two arms. I'm going to take a drink. This is a fantastic time for me to remind you that I would love questions if you have any throughout. And I know we've got a question and answer at the end, but this is really one of our favorite educational and outreach tools. So I hope that this.
Back about 1978, I attended National Science Foundation at LSU for physics, and we got to see Hamilton's
Did you really?
equipment.
Yeah.
He wouldn't let us go in there when it was working. He was in the process of chilling it down.
Yeah. Warren Johnson, he just walked into our office one day. He was like, "Hi, can anybody help me move something on the LIGO?" We're like, "Yeah, sure. You got it for sure." So,
What is that equipment still being used, or is it just mothballed?
No, it's not mothballed. I don't know. We care about it and we take care of it. No one's stacking books on it or anything.
Well,
But it's gonna be transported to.
Would it
to
make
LIGO
sense to
for
move it to LIGO and have it as an exhibit
That's
along
the
with your other stuff?
Yeah, that's the point. It's in the process of that actually. So I haven't the slightest, to be honest with you. But I do know that we were sitting on our hands for a minute. Not we, whomever.
I was just wondering, this Alcon, we were having a tour out there.
It's great.
And I was wondering if it might be out there by that time.
I would hope so. I don't know. I'll ask next time I'm there. End of July. Okay.
By the way, I haven't heard the rest of the lecture, so I might change my mind. But so far, you're explaining it better than some of the PhDs I'm doing something about it.
Thank you. Yeah. No. Let me know if something isn't.
That's a fantastic animation.
Isn't it great?
That's the best
Isn't it
one
great?
I've
Yeah.
ever seen.
This one. So
Oh my God.
That's a lot of potential error. If they're going to break, they're going to break on a well. And one of the ways we combat that uncertainty, we didn't just stack them like aluminum cans. You can kind of see here, just to the right of this first support ring, that diagonal piece of the tube right there is a spiral well.
Yeah.
These aren't just rings welded together; they're spiraled through a special jig. And this weld is apparently much more resistive to the kinds of forces that are being placed on it. Yeah.
I do understand that. I'm in the past, I've been doing stuff.
There you go. Yeah. So I hope they're up to snuff. But so that is done throughout the entire vacuum system. And then about every meter or so, these support rings are placed to give it a little bit of extra beefiness against that incredible pressure from the atmosphere. Yeah.
So I'm guessing you have sensors internally.
Oh yeah.
How is the vacuum maintained? There's got to be
Good
some
question.
leakage.
Good question.
Big soda straw.
So we have sensors everywhere. Data is the name of the game.
Yeah.
The detectors, on average, in plural, we produce about a petabyte of data. And we are constantly reading that, parsing through that, live updating that. We have to operate on the order of 16 kilohertz. We use analog electronics for almost everything. We're going to talk about that more in a minute. But we are constantly taking the vitals of the detector. All kinds of blood pressure, heart rate, if you'll excuse the analogy. And that is read not only live by an operator on site. If you go to the site, or if you've ever been for a tour, we'll take you into the nervous system, as it were. We've got screens everywhere, and one of the most important ones is the vacuum status. So we keep a very close eye on it. We don't spring big leaks. We do spring microscopic leaks, and those would get bigger and could get past even the most seasoned eye of a welding inspector, if I had to guess. But we have to keep very close tabs on it because we can't let it get worse. The vacuum system, when it was pumped down in the late 90s, in 1995, that was when construction began. It was pumped down like 1999. It took over a month to get the tubes to where we are now, and we needed to heat them to about 100 degrees centigrade to force out any water molecules that might have been hiding in the steel. After the vacuum had been pumped down, it has never been depressurized. That vacuum system is older than I am because it was incredibly expensive and time-consuming to get the detector to where it is now. Yeah.
I know you took the water out, which in Louisiana, we got lots of it. But I'm thinking most metals themselves, if I remember my chemistry correctly, will eventually, give some vapors off. I mean, that's just part of being a metal. And they're not totally as
Well, yeah.
solid as we might give them.
Yeah, void spaces.
So do they have to keep pumping to remove that too?
Well, that's a good question. So we are pumping always. You know, we have pumps on site that are regularly maintained and cross checked to make sure that when we need them, they're there, right? So it's but as far as evacuating, I have to imagine my first order guess. So I'll talk to engineers, but you know, if something were to enter the tube, even in a vaporous form, it would really screw stuff up. So I do think that if anything were to be, the pressure of this vacuum is such that we need to be like constantly tweaking it little by
What
little.
material, they use
They're
the
stainless steel.
alloy of steel or
Yeah,
what?
they're stainless steel.
Because you know what a Crookes tube is.
I don't.
It's not what you use to open a safe. It's basically an old demonstration, 1800s, and it's basically you use high voltage and you pass the voltage over, and as you pump it down with a high school pump, you'll start to see it turn sort of blue and so on. And eventually, when we get a really good high vacuum, all you'll see is a little bit coming off the electrodes.
Right. So that's actually interesting you mentioned. So another step of that vacuuming process was an ion pump to attract the particulate matter that wasn't so easily vacuumed up.
So they're using an ion pump.
They past tense, yes, they were. I don't think that's regularly in use, but I think that they've gotten to the place where they're happy. We are happy maintaining the vacuum little by little with our fine tuning, and then anything that is probably produced, if at all, will be removed in that same process. But I don't know. We're a little bit out of my depth, so.
Just there's some old stuff. I was lucky enough in the physics and chemistry room to find stuff that went back 20, 30 years, and I knew how to use it.
Right. Yeah, the state of physics department's demo closets should be a national study because we could use some new
That's cool.
reintegration.
I found one that was an X-ray tube, which
Yeah.
I never used.
Yeah. So the vacuum tube is really a tremendous testament to the capabilities of the engineers. And the fact that it's lasted so long, it is not by accident. People ask oftentimes, like, when are you going to turn it off? Like, when is it going to be? And we'll talk more about that. But really, the final say is when these tubes get out. We are going to be able to take interesting data for as long as these tubes survive. And thank goodness they have withstood the test of time thus far. So you can see here the arches of the protective coatings, right? These aren't just exposed to the elements. So when you go to the site, you'll just see these exterior concrete arches that are our environmental shielding. So protects us from things like the wind and the rain and the occasional bullet from a hunter who missed his mark on the hunting ground that we lease nearby. That's kind of an old wives' tale. I've only ever heard that happen once, but I do know I'm pretty good for it. So here are some of the vacuum components in the corner station. This one here in the center houses the beam splitter, and then these two house the input test masses. You can see here the enormous gate that we use to seal off the arms, which if you use your imagination, go this way, right? This is what we use to seal off the larger components of the vacuum when we need to do work on the middle stuff. We call these BSCs, basic symmetric chambers. They're gargantuan. You could stand up in them, no problem. I've seen RVs that are bigger than these, smaller than these, excuse me. And these are really the heart and soul of the detector. This is where the instruments live. And the things that are inside of those are our optics. This is the suspension system from initial LIGO in 2005. This is the end test mass. You can kind of see it. You can see the light glinting off of it. It's a cylinder, basically. It's made out of fused silica. And you can't really see it in this photo, but I promise it's true. It's dangling from a piece of the finest piano wire we could find.
That's the one they have on the city.
That's exactly right.
Yeah.
That's exactly right. Yes. We have it hanging from this superstructure, which super is a bit of a funny adjective there, and we'll talk about it why in a second. But we have it dangling in such a way to isolate it from ground motion. When you dangle something at the end of a pendulum, in this case, our mirror is we call it, again, the test mass. If the top of the pendulum moves at very high frequencies, then the pendulum bottom, the bob, stays still. This is our passive isolation, and that's for high frequencies, about a rumble per second, or about 1 hertz. So this is good for things like human activity and things that are happening on site, including earthquakes and really the disturbances that we think of more when we think of the ground moving. This was the initial suspension. So the seal fiber, I forget what diagrams I even have. So this is what we first used to combat against the motion of the ground at high frequencies. At low frequencies, we use more of those analog electronics that I'm talking about, operating at 16,000 times per second in order to counteract the motion of the Earth. So this would be sitting, you can kind of see the table here, sitting on a bed that would move in the opposite direction of the ground in order to keep the pendulum in the exact same position. So, decades worth of work, hundreds of PhDs, thousands of person hours, years of construction and commissioning, 2005 results, absolutely not. Absolutely not. We did not see a darn thing. That's okay. We knew that would probably be the case. Something that I forget quite often is when this was being built, we didn't have a great grasp on a lot of the physics that we were actually interested in, including how many black holes or compact objects even existed, including how often we thought a merger would happen if they did happen. There was still, just a modicum of doubt that we would never see. But thankfully, the National Science Foundation knew this. And around that time, around 2000, we actually began applying for funding for advanced LIGO. We finished building initial LIGO in 2005, and funding had already been approved. We were already planning upgrades after the initial observing run. And that's what we did in 2010. If my figures will load, awesome. So, a tremendous jump in technology from 2005 to 2010. This little suspension system here, scientists for scale, went to this. You can also see this exact structure at LIGO Livingston. It is, no exaggeration, 20 feet tall. And the test mats, also seen here, scientists for scale, quadrupled in mass from about 11 kilograms to about 44 kilograms. Those things cost about $50,000 a pop, so do handle with care, should you have a good chance. And our one-stage isolation, our single pendulum, went to 4 pendulums. One seen here, a second seen here, and then kind of like the boxy rectangular shapes our first and second stage. For each stage that we dangle our mass from, we gain like a factor of 5 in sensitivity. So this is pretty fantastic stuff. We also increased our laser power. The input power is about 800 times as powerful as my laser pointer. And it's still, I think it's like 8 watts, give or take. So very, very normal average amount of wattage. It's less than your average household light bulb by quite a lot. We then amplify that, we clean up the laser so it's nice and pretty, and then we send it into the interferometer at around 200 watts. So still not crazy. But then the real key is that it circulates in the arm about 300 times before leaving the arm. So as a photon enters at an energy of around 200, 150 watts, it cycles in the arm. So the power of the arm cavities is about 200 kilowatts. That's the stuff that'll fry you. So that's when you stand on top of the tube, when you go on the tour, we'll take you up. We have a bridge, of course, that goes over the top. But just knowing the circulating power that's happening, feet below you is really tremendous stuff. We also, around this time, welcomed Virgo to the collaboration. At the end of our second observing run was when Virgo came online as well. So it was really important that we build 2 interferometers to begin with, because we hadn't seen gravitational waves yet, and we wanted to make sure that they did exist. So if we saw a signal at Livingston, we needed to see a signal at Hanford as well. We also didn't know how fast gravity traveled. We had hypotheses, but having the distance between the sites was also very important, so that we could test the speed of gravity from one site to the next. More important, though, than that very interesting hypothesis, that question, is the isolation of noise sources. If there's a train impacting Livingston, I want to be far enough away that the train is also not impacting Hanford. And these things are very, very sensitive, so we needed to get them as far apart as possible. So Hanford was chosen first. It's a beautiful site on bedrock. Very windy there. There's not a lot of trees. It's in the arid parts of Washington that people don't often remember. And then Livingston was chosen second. It was top two between Louisiana and Maine. There were scientists, including Hamilton and Johnson, who built a LIGO. They kind of put in the bid to say, please build it here. They put in a very convincing proposal that including LSU as a sponsor of the site, a host of the site. They said, we're going to hire 2 faculty members. Those faculty members will bring in graduate students. They'll bring in postdocs. We will provide support to the site. We found you land. There are photos of them with like survey sticks out in the boonies of Louisiana.
They actually donated the land, which is one of the things that
I think that's true. And this is the funny part because everybody tells a different story, and I love it. Like, I would love to get the one pin down that's true beyond the shadow of a doubt. But it really does read like a fairy tale. Why did it happen here? When I give tours at LIGO, that's really the question a lot of local Louisianans love to ask. Why here? Why in my backyard? Why in Livingston, Louisiana? And the answer is because the scientists were so fervently involved in convincing the legislators that we could do it, that we will bring in the people, we have the land, we're far enough away from the first site that you've already chosen. Like, please build it here. It was down to here in Maine, and the story I've been told is that the senator in charge of appropriations at that time was from Louisiana, and maybe gave it a little nudge in our direction. I've never confirmed that. Yeah, exactly, right? So, but, I always tell people that, I get a laugh. But really, the answer is that the scientists at the time were really heavily entrenched in gravitational science and produced a very convincing case for Livingston as the host site. So obviously it got built, and the 2 faculty members that they hired at the time are Joe Gianni, who is now director of LIGO Livingston, and Gabby Gonzalez, who was spokesperson for about 10 years and is my PhD advisor.
that both of them are students.
That's fantastic. You can be.
Joe came here in April.
Really?
16, yeah.
Yeah, that's right after the detection. Yeah, that's right.
I was at this auditorium when they made the announcement.
That's right. Yeah, I wish I could have been around for that.
Did I understand you correctly that this could actually, it's not measure earthquakes, but would they be the earthquakes you would especially find deep inside the earth?
No, we see every earthquake, really.
So it's something to be used for the core of the earth.
No, it's mostly we have like the USGS site pulled up in the control room. We're like, all right, earthquake happened in Taiwan. It should be here in 20 minutes. So, no, it's really just the things that our other people are monitoring as well. So in September of 2015, we reversed our fortunes and detected for the first time directly gravitational waves. This is gravitational wave 150914, so 2015, September 14th. It's a beautiful signal. It's about 30 solar masses of each component combining into around a 59 or 58 solar mass black hole. You're saying, Zach, 30 plus 30 doesn't equal 58. That's true. About 2 to 3 solar masses worth of energy were lost in the merger. It was so much energy, in fact, that if you froze time for the split second after the merger, added up all of the energy from all of the stars in the observable universe, and added them together, it still would not have been as energetic as our event was. So this is truly one of the most violent, powerful events we have ever observed. And it only moved our mirrors by 1/1000th with the proton.
Unreal.
So shown here in the darker color is the actual data from the boulder, if you will, is the actual data from the detector. And the predicted is the thinner line. So those are simulations run on supercomputers with Einstein's equations that say, if a 30 solar mass and a 29 solar mass black hole merge, here's what the waveform looks like. So we use these waveforms, these predicted waveforms, to search for gravitational waves through a method we call matched filtering. We're constantly combing through the data, running these waveforms against what we observe. And when they match up, the math is such that it produces a spike in signal to noise ratio, and our automated pipelines, sing our praises and say, hello, please, we found a gravitational wave. Please investigate it more. This one, of course, was not sent out to the public immediately. Lots of double checking, data validation, and paper writing went in before it was announced in February. We'll do that one next. But now our algorithms are such that when we detect a gravitational wave, the scientists in the collaboration can learn about it at the exact same time as the general public. We have a database we're going to talk about in a little bit, but it's not behind closed doors. It's not behind lock and key. We try to get this information out as soon as we can to the relevant and interested parties. So I don't know if we have sound, but let's see.
Yeah, I don't think so.
Maybe.
The speakers for this.
So you're going to hear two sounds. The first one is really quite low. You're not going to believe me when I say that it is the sound of the gravitational wave. And then the second one is the higher pitched one that you just heard. That is what we mean when we say we are listening to the universe. We don't say it to be esoteric. We don't say it to be unique. These mergers are happening in frequency ranges that our human ears are sensitive to. So even though, I can't necessarily discern a ton of interesting physics from what I just played you, by golly, is it cool. No one else is observing the universe in the way the LIGO collaboration is. We can run 24/7, 365. We're not subject to things like cloud cover or, that's my only example. But this unique lens through which we can view the universe is not a competitor to optical or X-ray or neutrino or anything like that. This is really just, we've never had a perspective like this before that allows us to work in tandem with these established fields of observation. And that's exactly the point we made in February of 2016 when we announced the discovery with the National Science Foundation. That's Kit Thorne. You guys probably know who he is, very well-known physicist. This is my advisor, Gabby, and this is the director of the National Science Foundation at the time, from Cordoba. And these are the laureates of the 2017 Nobel Prize. So there was one thing. You guys have me off my flow, which is a great question.
Well, so I was thinking about this. Any thoughts on, I guess the right way to describe it's fingerprint of a gravitational wave, consistency between different events?
Yeah, great question. They're like snowflakes.
That's what I figured.
That's exactly right. That's exactly right. That's a fantastic question. And the best point I have to illustrate that is let me get there. That's a great question. So if the GIF will play, that'd be cool. That wave, 150914, originated about 400 megaparsecs away. That's 1.3 billion light years. Because gravity travels at the speed of light, it is no stretch of the imagination to explain that gravitational wave was traveling through space for 1.3 billion years before it happened to hit our detector. Earth was nothing but a hot ball of water at the time. The continents hadn't formed. Humans certainly hadn't begun to evolve yet. And we were so fortunate to not only evolve into the intelligent beings we are today, but develop the technology, the understanding, the math, the lasers, to put it all together into one piece, to turn it on at the exact right time, to see this gravitational wave event from 1.3 billion years ago. That is tremendously humbling and just fantastic to think about. The laser was invented in the 60s. Einstein died in the 40s. So if you had told him, hey, we're going to use a laser to detect your theory of gravitational waves, I'd like to think he'd ask you what a laser is. And when the person who invented the laser produced this discovery for the world, I don't think he would have thought that we would be using it to scan barcodes at the self-checkout, let alone send it down an 8-kilometer-long round trip to detect black holes merging from 1.3 billion years ago. But we did do exactly that. Einstein predicted what he needed to predict. The inventors of the laser invented what they needed to invent. The opticians created the optics that we use. Everything coalesced perfectly for us to detect what is still the largest peak-to-peak amplitude gravitational wave event that we've ever seen. So 1509-14 is really special to a lot of us for a lot of reasons.
If you're interested, Einstein might have caught on very quickly since he won his Nobel Prize for the photoelectric.
That's true. That's true. Yes, I'm stuck. So to date, we have detected 90 gravitational wave events. This is actually outdated, which is cool. This is the first time I've been able to say this. We've seen more since then because the detector turned on. Last time I gave this talk, we hadn't begun observing yet before observing. That has changed. We began at the end of May, and we have seen several gravitational wave events since then. So that's pretty fantastic. If I had to guess, we're up to about 96 right now, which is great. Each of these black holes or these mergers is truly unique. You read this plot, it's the lower two dots follow the arrow and they merge into the third dot. So, a 8 and a 12 add together to make a 20 solar mass object. So that's what we're seeing here. The orange ones are neutron stars. The blue ones are black holes. And the orange and blue ones are a dirty little secret of the collaboration because we don't know what they are. These have masses such that they are either the lightest black hole ever discovered or the heaviest neutron star ever discovered. We're not sure. And we need more data to figure out which is which, but they're events nonetheless. If you want to learn more, the GRACE database, Gravitational Wave Candidate Event Database, is our one-stop shop for information dissemination to the public. We also use this internally in the collaboration. This is not well, it kind of is a toy. It's awesome. It's great. You should use it for everything. And you've also got an app. Do you have the app? Yeah. We have an app that will chirp at you every time we detect a gravitational wave. So I like this one because it has great. That's yeah. Our science education team is truly second to none. But this is where we go for all of our events. So again, 230612, that's an event from June 12th. And then we also will put probabilities of origin. So these last two are definitely not gravitational waves. So we're constantly publishing. And then sometimes we do have to retract. But we thought that the investment versus risk versus reward of getting the information out quickly was worth a little bit of, hey, sorry if we have to pull them back. So gracedb.ligo.org, that's where I get all my information and where you can too. So 90 gravitational wave events, but I would be remiss if I did not talk about one very special one, which is the one I have circled in red here. It's a binary neutron star merger that happened August 17th, 2017, and it is the only event to date with an electromagnetic counterpart. A gravitational wave event that we detected and was followed up shortly thereafter in all bands of the optical, gamma, all the way down to radio. This is a very special event to a lot of LIGO collaboration members because it's our only one. So we managed to get a localization. I don't remember the area off the top of my head. I want to say it was like, no, I'm not even going to try. There were about 40 galaxies in the area that we gave astronomers, and they needed to go and tile them before they could find the source of this event. And what they found was that about 20 days before the merger, there was nothing in our crosshair here, but 10 hours later, we had a new pinprick of light in the sky, and that was the kilonova from the merger of these two neutron stars. Events like those are incredibly useful, not only to us as a collaboration, but also to astronomers and other fields of physics. Because these neutron stars are so dense and so hot and so energetic, these processes very closely mimic that of the early universe. We don't have a direct analog quite yet, in any capacity really. So catching these early and catching these often and getting things like decay lines and production rates of these elements, including like R process elements, rapid capture process elements, is really, really important to understanding the origin of heavy elements, the synthesis of elements that took place at the beginning of time. These are very key to unlocking a lot of very interesting physics and a lot of very interesting fields. So a lot of time and effort has been made to improving things like our sky maps for astronomers, our latency to getting that data available, and our cooperation with collaborations like Fermi and other gamma ray telescopes. So that's the beginning of multi-messenger astronomy. To so many people, that's the name of the game. Being able to detect our merger, and then seconds later, the gamma rays from that same event. This is the first time anything like that had ever been done, observing one event in multiple messengers, messengers being gravitational waves, electromagnetic radiation, cosmic rays, and neutrinos. And we saw all of those with 170817. I'm trying. So this is every event that we had seen until just recently. And then the color here is power, right? So the more colorful it is, the brighter it is, the more powerful it is. You can see here, that's 170817 right there. Very long template, very long signal because it's low mass. They're going to end spiral way longer than something like a binary black hole with higher mass, which could appear, you know, in a split second. We've had binary black hole mergers that have taken less than a second, no problem. And really, this is what I wanted to talk about. You know, each individual snowflake of an event. I mean, you can see it visually. No two of these are exactly alike. And you know, even though we have seen far more black hole mergers than we have anything else, we're still so interested in them because they're so unique. So we don't have a set target number of events that we want to detect. We're going to detect for as long as we can, as accurately as we can, so we can continue to build our knowledge of these events and these sources. We have seen more black holes than any traditional optical observational technique has, just because they're easier for us to see. Imaging something like Sagittarius A star is really, really quite difficult, even observing in X-ray. So we do have that advantage to help our statisticians come up with population models to estimate how many black holes should exist, where they should exist, how heavy they can be. So adding to this data set is our priority, and I'm very happy to report that we've been doing just that at the beginning of the fourth observing run. So looking ahead, this is, again, an outdated slide, but like in a fantastic way. It's not too terribly outdated. Actually, this plot is from today. This is our range. This is how far into the universe we can see in megaparsecs on the y-axis, and this is just a time series in universal coordinated time. And the blue line is where we were in the third observing run. So we've improved by about 20 megaparsecs, which is fantastic. So that means our observing volume has increased by a factor of 20 to the third because we have a sphere centered on Earth. That's fantastic. This is the best way we have at observing more events. It's just increasing our range, getting more sensitive, getting us a bigger volume at which we're sensitive to. We did that due in no small part to frequency-dependent squeezing, which is a graduate lecture course in and of itself. You'll hear a little bit more about it if you went to LIGO Livingston, but really what we're doing is leveraging quantum mechanics in favor of us rather than against us. There's an uncertainty principle there between phase and amplitude. Phase and amplitude, respectively, at low and high frequencies, like dominate your noise source. So if we can reduce one, we have to spin it in the other, but we can do that now at different frequencies. So we can squeeze in phase, increase in amplitude at low frequencies, and squeeze in amplitude, increase in phase at high frequencies. I said that backwards. But we're able now to reduce noise as a function of frequency rather than having to pick to one and stick with it for the whole observing run, which is what we had to do in 03. And then we also developed, this is from our March meeting in Evanston, Illinois, Northwestern. We have an incredibly robust team. This is like 300 people, I think 400 people. We have 1,500 scientists in that collaboration, spread out over the entire world, dozens of universities. It really does take a village to raise these two interferometers, and we love them deeply. It's like getting to know a person, learning to work on these things. And there really is a lot of love that goes into making them the best possible versions of themselves that they can be, so that we can see farther, be more sensitive, get more events, continue to learn more in our very unique lens with which we have the privilege of viewing the universe. And a lot goes into that. This is probably the most simplified diagram of our interferometers that I could find that wasn't just like an L shape, right? So we've got squeezer teams and optics teams and laser teams, and it really is just amazing that it all gets done, if nothing else. Everybody does their job so that we can continue to produce these events for the public, for other astronomers, and we can continue to learn together. So I think the easy thing for me to say, and if you share this disposition, no worries if you don't, but I so often think like, oh, what if we had the detector 10 years earlier? What if we just had the second brightest gamma ray burst of all time in October? The brightest gamma ray burst of all time was in October. And an LSU faculty member gave a press conference about it. Like, what if we had been observing 6 months earlier? Can you imagine what we would have seen? It's very easy for me to fall down this slippery slope of what ifs and maybe a little bit of discouragement, because we can't run all the time. We need to be more sensitive. We're not sensitive enough yet. But I remind myself that first event, 150914, traveled for 1.3 billion years before it finally smacked into our mirrors and changed our arm lengths just enough for us to detect it. And when I remember that whatever fantastic event that we are going to detect in the next month, 6 months, year, decade, it's already on the way. And who knows what's already headed for us now. So thank you very much.
Hopefully not in nearby GRB.
That's what I'm thinking the same thing. I'm hoping nothing's going to be closer than a few 100,000 light years or farther, because I don't want to be around when a gamma ray burster goes off close to us.
If that's how we all go, that's fine with me.
It'd be quick. It'd be quick.
Yeah.
You won't have to think about it long.
Exactly. That's right.
Well,
So I'd
the
love to
people on
take
the
any
other
questions.
side of the earth from it will have a little bit longer,
It's true.
but not much.
How well is the temperature controlled in the arms?
It's room temperature. It fluctuates. So
So
Kagra in Japan is cryogenic. It is cooled.
So the variation in the arms does not affect your measurement.
Because we pump out that air. Temperature fluctuations need to travel through something.
But the metal expands as temperature.
Yes, but we're broaching into my going beyond my means here, but I'm sure that had to have been considered, right? Especially given the Louisiana heat, the expansions and the contractions had to have been controlled. Plus, within those basic symmetric chambers, the tubes might do what they do, but that's not impacting.
Right, because they're suspended.
Right, exactly. Yeah, they are as isolated from the Earth as we can get them. Do you have a question?
Yeah, how do y'all determine the collaboration? Say y'all collaborate. Yeah, how do y'all determine that?
In what sense? Like who gets to become a member?
No, like you do. You say that satellite that you use,
Yeah.
and collaborate between that to get the different, types of
Sure.
Yeah.
Lots of politics and diplomacy, I think. It's multifaceted, right? Because we have 1,500 people in the LIGO collaboration. Full stop. So not even Fermi or Integral or SWOPE or JST. So we have to stay central first, and we have leadership, we have a hierarchy, we have elected officials that keep us all in line and make sure that the graduate students are doing what they're supposed to do, and we have institutions that sometimes need to leave the collaboration because they can't pull their weight. And it is a mutual understanding that when you join the collaboration, you need to produce more accurately. We don't need 10 papers a year or whatever. We just need your help. So I don't know that the application process is particularly strenuous. Bless you. I just do know that it is like a continued commitment. And then of course when we I think it's in everybody's best interest between like us and the satellites, right? It's like we need to be on the same page. And I think we really accomplished that by being like, here is the data we have. We don't cherry pick the data. We don't withhold anything. We send everything we have as soon as we can, so that satellite teams can get on sky, so that ground-based astronomers can get a cup of coffee and go point the telescope. We just try to be as forthcoming as possible, as communicative as possible, to make sure that we are all on the same team here, and that same team is advancing science. Yeah.
So when the neutron stars collided, why did it only move the mirrors a tiny bit if it was a huge amount of gravity?
Good question. So their gravity would be less than the gravity of a black hole collision, right? Because the neutron stars are lighter than the black holes. But because gravity is just so weak, that even something really amazingly powerful like that only moves our mirrors like less than you and I can imagine. Because of the fundamental nature of gravity that like we really don't understand yet. We just know that gravity is weak, and because of that, it can't move stuff on Earth alone.
And then how does our Earth orbit the sun on gravity?
Great question. Great question. That's what's that?
I was gonna say, I hope it's orbiting.
Yeah. It's because those gravitational waves have to travel really, really far, right? But they're really good at not losing energy, so they can go for a very, very long time. The sun is very heavy and stretches. Here I go, clicking a million times. Let's see how fast I can do it. Aha.
There we go.
When the sun, if you imagine the sun being here, right? The sun is very, very heavy, so it stretches space more than the Earth does. And the Earth just kind of sits on this rim right here. So even though the sun's gravity is weaker in comparison to something like a black hole, it's still more than enough to keep the Earth orbiting.
Because it's closer.
Yes, and because of the way that it stretches space-time, but being close definitely helps. Yes, good question.
Is this what you want to do the rest of your life?
Yeah, for sure.
I just want to know because this is a long time project. You could probably retire with it.
Oh yeah, no, yeah. This is a little bit of a personal interest. I'm an accountant actually. No, yeah. So yeah. I mean, we have proposals for a 40-kilometer long U.S.-based detector, a 6 interferometers as V shapes, and the orientation of a triangle in Italy or in Europe, but they're still trying to decide the site called the Einstein telescope. They're sending up LISA in 2037. They're trying to build an interferometer on the moon. Like, I've got no shortage of projects to pick from if I decide to stay in science, which all roads seem to point to that. So, yeah.
I had a further question about the collaboration.
Sure.
I know we've got, Hanford up there in Washington, and
That's right.
Japan and stuff now. You said, we have over 90 detections.
Mm-hmm.
Were all of those detections made from here, or some of them were made up in Washington first, or in Japan first, and we just all, collectively
Just talk about it.
Yeah.
Right.
Yeah.
Good question. So you could really think of Livingston and so Louisiana and Washington are like twins. Like we do not fight.
That's
We
another question too, is when they upgraded to advanced light.
Oh, it's both of them. Oh yeah, 100%. It's very important that they be exactly the same as best we can. So it wasn't as if Livingston was like, we'd like one please, and Hanford was like, ooh, us too. Like when we submitted the proposal, it was both or nothing. And then, as far as interferometer experiments go, there aren't that many of them. So when you build one, you're searching for the same things, really. So Virgo is a little bit different, and Cagra, of course, is quite different. But whether or not we swap notes at lunch about our suspension systems, no one's gonna like keep it from another collaboration. But I think people do want to go their own ways. But if we detect something, it far and away benefits everybody to go all in and say, here's what I have. And more so, 170817, the only electromagnetic counterpart that we've ever seen, Virgo didn't see it. Not that Virgo was down, not that Virgo was damaged. It was not in Virgo. It was in Virgo's blind spot. No, it was.
What, the
It
right
just-
frequency?
Yep, if Virgo was oriented correctly, it could have seen it, but it didn't. So that told us if Virgo didn't see it and Hanford and Livingston did, that narrows down our search window. Exactly. So that was really important for us to actually be able to reduce, I think by like half, the amount of sky that we sent to astronomers to say, please tile this as quickly as possible. So do we compete internally? Absolutely. Livingston is way better than Hanford. But you know, everybody has their quirks. We're a little angry with Virgo right now because they're joining us in the fall. So, I mean, we understand. It's hard. It's hard what we do. So it's not, you know, we don't kick other scientists when they're down because we are trying to do the most precise measurement in human history, the pinnacle of human engineering, and I would go so far as to say collaboration, just at the damn scale of the thing. So
Back to well, like the amount of detections that we got right now, like at least between us and Hanford, is
right.
that like
good question.
It's you know, I know the first one was they said we got it here.
We got it here first. That's right. That's right. Depending on the, you know, if I'm the center of our observing sphere right now, it can come from anywhere, right? The detectors are most sensitive in the Z direction, X, Y, Z, just because of geometry. Thank you, physics. So we do have, I think actually in the fourth observing right now, single detector events. We have the capability, we know gravitational waves exist, so we don't necessarily need a coincident event at both sites. Is that good? Sure, just as a double check, but we've seen enough now that our algorithms know what to look for and can be confident we can expand our search areas just enough so that they don't necessarily have to overlap in all versions. So if Hanford sees something and Livingston doesn't, because Livingston's maybe down, or I mean we lose lock several times a week. Just we can't help it yet. So you know,
for further clarification,
sure.
Those 90 that you were, or more than 90, those are just like ones that Livingston has detected, like maybe Hanford has detected fewer, or some that we haven't, or they just count the same ones that we got that they counted it to. Like, you know what I mean? It's like we've detected 90 from here, but
right.
we detected
87, right? It's pretty generally agreed upon. It's a we thing. If we, the collaboration, have written this paper where we say we have found, literally we, my name's on it, you know what I mean? We have detected 90 gravitational wave events. Are some of them less likely to be gravitational waves than others? Sure. If you gave me $1 million to put on red or black, is every gravitational wave an event? The gravitational wave signal that I showed you an event or not? It's no. It's no. I guarantee you there's one there that is not a gravitational wave event. We don't necessarily have the tools to go back and comb through yet. I bet we do. We will eventually. But it's you know, we're confident as best we can be now that we, the collaboration, have detected 90 gravitational wave events plus like the 6 or whatever I've talked about. Some of them might be. I think we had one single detector trigger in that paper, and I think we had one event. We were like, only one detector saw it, but like it's a gravitational wave. I think that number differs between like the U.S. sites and Virgo. And Cagra for sure, because Cagra only came online for a little bit at the end of 2003, and they had a very, very tiny observing volume, like 1 megaparsec, I think. So there are definitely some between Livingston and LIGO and Virgo that will mismatch. And of course, I mean, there are teams as we speak going through our data and being like, ooh, you missed one, ooh, you missed one. We might have, that's fine. But that's why we make all of our data public. Please go and find more. That would be great. So when we say things like that, when we put out a paper, LIGO collaboration, it is we, the royal we, and we're pretty proud of what we found. Good question. Yeah.
I was looking at an article dealing with the web using gravitational lensing. Look at some of the earliest objects in the solar system. And it clicked to me with your talk. It's probably beyond our ability to do anything now, but if there's lensing of light, isn't there also lensing of gravity waves? Could they be lensed around some of these objects? And if you can, I don't know, and it has sense enough or piece of equipment, could you actually look back for gravity waves close to the beginning of the universe.
Yes, 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 there are collaborations that want to do that, yes. There's a group called Nanograv. They use pulsar timing, rapidly rotating neutron star using the Lighthouse effect. The arrival time of the pulsar signal will be ever so slightly impacted by the presence of primordial gravitational waves. They have a paper coming out soon, so I've been told, year round. I don't. It's not supposed to be like ground. It's a very big step forward for them, which is fantastic because that's stuff that we're never going to see, right? Like we have a spectrum of gravitational waves, from the very very small primordial ones to the gargantuan ones that we hope to see. So I don't know if gravitational waves could be lens themselves. My guess is no, because I think it needs to interact with something massive. So I think if you could create a gravity well without mass, I don't think it would impact the gravitational wave. But by golly, that's an interesting question.
Galaxies early galaxies colliding and
Sure,
things like that.
sure. Yeah, I mean,
That's-
we're looking for all kinds of different sources. Supernova should produce them. An aspherical, a neutron star rotating very rapidly that's deformed on the order of inches will produce a gravitational wave. So we're looking for those continuous
I'm just thinking,
sources.
back
Yeah, we're looking. Yeah, there will be
10 billion
yes,
years back.
Yes,
maybe,
yes,
something
yes,
like that.
absolutely.
So in
That-
theory, you could see an object, you could see something that did not involve a merger.
oh yeah, absolutely, for sure.
That would be interesting.
Yeah, we have these burst searches all the time because those look a lot like glitches, right? If a supernova goes off, it kind of looks a lot like a glitch to me in our data. But yeah, we have these other sources that we're very interested in. I should
Interesting.
You have some.
So, I've read that proximity to different masses could theoretically affect the perception of passage of time for different observers.
Sure.
Is that because of the curvature of space-time?
Yeah, well, first of all, let me say that it's 100% true. That clocks on airplanes run ever so slightly different than clocks on the ground. And if we didn't account for general relativity, clocks running different as proximity to masses, in our GPS satellites, you'd be off by about 6 miles if we didn't account for that. So that's one of my favorite things, and I wish I should have emphasized that more because it's true, and that's like the basis of what we do. And it is exactly because of the presence of mass. Yes. When I show this X and Y cross hatching, one dimension is the space, and the other dimension is time. So when a gravitational wave passes through you, not only so it squeezes in one direction and stretches in the other. So there's a running joke that you can't defend a PhD thesis, which I'm doing without doing. Let me think about it. This, right? I'm squeezing up and down and stretching in the opposite direction. But not only does space do that, but time does that as well. So as a gravitational wave squeezes and stretches, part of me is me to you to the ceiling to the floor is running in different times because of the nature of the interconnectivity of space and time. Yeah.
This is too
Come on,
much.
thanks, Zach.
Yeah, thank you.
That's awesome.
Give you a little practice for your dissertation.
I still got 4 years, but I'll remember this one.
Okay, well, come back and talk to us every year.
I will,
And let us
yeah,
know how
yeah.
you're doing.
There's something, hopefully I'll have something interesting and new every time. I went a little long, so sorry about that.
That's all right.
Oh, you're
I don't
We're in
know.
no rush.
You got into live streaming now?
yeah. If you go ahead and say goodnight to the folks at home, we'll stop
okay.
that and we'll continue the meeting.
I want to say goodnight then to everyone who's online here and who will be viewing this video. So we'll say goodnight and see you next month then.
And we apologize for any audio issues that
Right.
happened during the
Yeah,
early
that's
part of
right.
the presentation.